Hello, welcome all. Today we are going to discuss perturbed circular orbit and planetary motion. They are the cases of central force motion. A satellite of mass m orbits the Earth in a circle of radius r0. One of its engine is fired briefly towards the center of the Earth, changing the energy of the satellite but not its angular momentum. The problem is to find the new orbit. ഒരു ഉപഗ്രഹം ഭൂമിയിൽ നിന്നും വിക്ഷേപിച്ചു. അത് ഭൂമിക്ക് ചുറ്റും ഒരു വൃത്താകൃതിയിൽ കറങ്ങിക്കൊണ്ടിരിക്കുകയാണ്. One of its engine is fired briefly towards the center of the earth. അതിലെ ഒരു എഞ്ചിൻ ഭൂമിയുടെ മധ്യത്തിലേക്ക് തിരിഞ്ഞുകൊണ്ട് ഫയർ ചെയ്യുകയും ചേഞ്ചിങ് ദ എനർജി ഓഫ് ദ സാറ്റലൈറ്റ്, ആ ഉപഗ്രഹത്തിന്റെ ഊർജം എനർജിയെ മാത്രം ചെറിയ മാറ്റമുണ്ടാക്കുകയും ആംഗുലർ മൊമെന്റത്തിന് മാറ്റമുണ്ടാക്കാതിരിക്കുകയും ചെയ്യുന്നു. എങ്കിൽ ദ പ്രോബ്ലം ഇസ് ടു ഫൈൻഡ് ദ ന്യൂ ഓർബിറ്റ്. ഈ സാറ്റലൈറ്റിന്റെ പുതിയ ഓർബിറ്റ് എന്തായിരിക്കും? നെക്സ്റ്റ് സ്ലൈഡ്. So the corresponding energy diagram for this problem. The energy diagram shows the initial energy and the final energy. You can see from this graph the initial energy and the final energy. That means before firing the energy of the satellite is EI, and after firing the energy of the satellite is EF. Note that the firing the engine radially does not change the effective potential because L is not altered. Since the Earth's mass ME is much greater than M, that is satellite mass, the reduced mass is nearly M and the Earth is effectively fixed. അതായത് ഭൂമിയുടെ മാസ് വളരെ കൂടുതലായതുകൊണ്ടും സാറ്റലൈറ്റിനേക്കാളും the reduced mass is nearly M, അതുകൊണ്ട് ഭൂമി എപ്പോഴും അവിടെ പൊസിഷൻ ഫിക്സഡ് ആയിട്ട് സെന്റർ ഓഫ് മാസിന് മാറ്റം ഉണ്ടാകാതിരിക്കും. മാത്രമല്ല എഫക്റ്റീവ് പൊട്ടൻഷ്യലിന് മാറ്റം ഉണ്ടാകാതെ ഫയറിംഗ് കൊണ്ട് ഒരു എഫക്റ്റീവ് പൊട്ടൻഷ്യലിന് മാറ്റം ഉണ്ടാകാത്തതിന് കാരണം L is not altered. L എന്ന് പറയുന്നത് angular momentum is not altered. Next slide. Angular momentum of the satellite is not altered. If EF is not much greater than EI, the energy diagram shows that R never differs much from R0. Rather than solve the planetary motion problem exactly as we do in the next section, instead approximately U effective in the neighborhood of R0 by a parabolic potential. അതായത് final energy of the satellite is not much greater than the initial energy. സാറ്റലൈറ്റിന്റെ ഫൈനൽ എനർജി ഇനിഷ്യൽ എനർജിയേക്കാൾ വളരെയധികം കൂടുതലല്ലെങ്കിൽ ആ ഡയഗ്രത്തിൽ നിന്ന് നമുക്ക് കാണാൻ സാധിക്കും ന്യൂ പൊസിഷൻ ഓഫ് ദ സാറ്റലൈറ്റ്, ആ സാറ്റലൈറ്റിന്റെ പുതിയ ഓർബിറ്റ് എന്ന് പറയുന്നത് R0 നിന്നും വളരെ അകലെ ആയിരിക്കുകയില്ല. അങ്ങനെയുള്ള സന്ദർഭത്തിൽ we can solve the planetary motion problem exactly. Planetary motion problem നമുക്ക് solve ചെയ്യാൻ പറ്റും. As we know from our analysis of small oscillations of a particle about equilibrium, the resulting radial motion of the satellite will be simple harmonic motion about R0 to good accuracy. Small oscillation എന്ന് പറയുന്ന ഒരു തിയറി ക്ലാസിക്കൽ മെക്കാനിക്സിലുണ്ട്. അതനുസരിച്ച് ഒരു ബോഡി ഓസിലേറ്റ് ഒരു പോയിന്റിൽ നിന്നും ചെറുതായിട്ട് ഡിസ്പ്ലേസ് ചെയ്തെങ്കിൽ ആ ഡിസ്പ്ലേസ് ചെയ്ത് സ്മോൾ ഓസിലേഷൻ നടക്കുകയാണെങ്കിൽ അതിനെ നമുക്ക് വീണ്ടും സിമ്പിൾ ഹാർമോണിക് മോഷൻ അബൌട്ട് R0 അബൌട്ട് ഓഫ് എ ഗുഡ് ആക്യുറസി അപ്രോക്സിമേറ്റ്ലി നമുക്ക് അങ്ങനെ ഒരു അപ്രോക്സിമേഷൻ നടത്താൻ സാധിക്കും. ഇപ്പോൾ ഈ സാറ്റലൈറ്റിന്റെ കേസിൽ എടുക്കുമ്പോൾ എഫക്റ്റീവ് പൊട്ടൻഷ്യൽ എത്രയായിരിക്കും എന്ന് നോക്കിക്കഴിഞ്ഞാൽ ആസ് വി സ്റ്റഡീഡ് ഫ്രം ദ പ്രീവിയസ് വീഡിയോസ്, the effective potential is the kinetic energy in the angular direction plus the potential energy due to the gravitational force in this case. അപ്പോൾ കൺസർവേറ്റീവ് ഫോഴ്സ് എന്ന് പറയുന്നത് ഗ്രാവിറ്റേഷണൽ ഫോഴ്സ് ആയതുകൊണ്ട് പൊട്ടൻഷ്യൽ എനർജിയുടെ അല്ലെങ്കിൽ പൊട്ടൻഷ്യലിന്റെ എക്സ്പ്രഷൻ എന്ന് പറഞ്ഞാൽ -GMM/R. ഇവിടെ -GMM C ആയിട്ട് കൺസിഡർ GMM-നെ C ആയിട്ട് കൺസിഡർ ചെയ്യുന്നു. സ്മോൾ m is the mass of the satellite, capital M is the mass of the earth. So minus GMM/R is minus C/R plus L square by 2 mr square is the kinetic energy due to the angular component, that is angular direction. This is also added in the effective potential energy term. Now at the R0, that means where there is a minimum of the potential energy curve, that is at the value of minimum of the U effective potential obtained is R equal to R0. Now at that minimum, the slope is 0, and therefore we can equate the first derivative of the effective potential to be 0. So once we differentiate this equation, and when we equate it to 0, so if we differentiate minus C by R, we'll get minus of minus 1 by R square into C. And if you differentiate 1 by R square, these are all constants, L square by 2m is constant. So it will become minus 1 by R cube, and 2 will come, that will cut out. So the answer is, this is the differential C by R0 square minus L square by m R0 cube. Next slide. And if the frequency of oscillation is denoted by beta, then we can say beta is equal to root of k by m, where m is the mass of the satellite and k is the value of the force constant, which is here denoted by, at the minimum value, the second derivative of the potential, effective potential, is what we call as the spring constant. And this, if we put the value of k in the beta expression for the frequency of oscillation, beta is root of, put the value of k, that is k is d square u by dr square, and that is calculated to be c by mr0 cube, and that is equal to L by mr0 square. So this type of equation, the solution is given by, because this is a second order differential equation. The second order differential equation has a general solution, a constant R0 plus a sine beta t. This is the general solution of a second order differential equation. And coming to the next slide, we have omitted the term b cos beta t in order to satisfy the initial conditions R0 equal to 0, because as at the initial point, the satellite was assumed to be at the distance R0, that is at the minimum potential. So at that case, the value of R0 is just R0. In that case, the term b cos beta t is omitted. Although we could calculate the amplitude A in terms of E effective, we shall not bother with the algebra here to note that for R0 very much greater than A, for EF nearly equal to EI. Since we assume that the final kinetic energy is also very close to the initial kinetic energy of the satellite, initial total energy of the satellite, we can leave that discussion also. Now we are going to find the new orbit of the satellite. So we are going to express the angle, that is theta. For the circular orbit, as we know, the angular velocity theta dot is given by L by m R0 square. So in this case, theta can be found from the next slide. In this equation, this is enough for the accurate for our purposes. The radius oscillates slightly after the engine is fired, and the time in a time which is very small, and we are neglecting higher order terms. See, the frequency of rotation of the satellite around the Earth is given by, that is omega, it is theta dot, that is d theta by dt, that is L by mr0 square is equal to, putting the value of this L, root of mcr0 is equal to c by mr0 cube, and from that we get the value of theta, L by mr0 square into t, because you can see here this theta by t is nothing but theta dot, that is omega. So I multiplied t here, and this will become beta t. The beta is the value given by L by mr0 square, which is a constant. So the frequency of rotation is identical to the frequency of the radial oscillation. That means the satellite's orbit is oscillating, which is similar to the frequency of rotation. And from this figure, you can see this is the equation that represents a particle moving in a circle, and that is the same equation we got in this case of the satellite's orbit. So this is the old orbit and new orbit. The new orbit is shown as a solid line in the sketch. You can see the solid circle is the sketch of the new orbit, and the old orbit is shown in dotted circle, but both the orbits look similar or circular, and it is no longer centered on the earth. The only thing is, you can see that the new orbit is not centered on the earth, whereas the old orbit is centered on the earth. The exact orbit for E is EF is an ellipse with the equation. Actually, it is an ellipse with the r is equal to r0 by 1 by a by r0 sine theta. That means if I have not neglected the value of a, this will be the equation of that new orbit of the satellite, and that would be a ellipse. Since I have neglected the term a by r0, that is very small compared to 1. So comparing to this 1, I can neglect this term, so that will become, the denominator will become 1. So if I have not neglected the value of a, because the a is nothing but the distance between the circumference of the two circles, that means orbits. That means the width between the two orbits is what a refers to, and that you can again from binomial expansion 1 minus, this is very small value, if you go up 1 minus x raised to minus 1, that will become 1 plus x. So approximately r0 plus a sine theta, that is what the orbit of the new orbit, a satellite of orbit of the satellite after the firing. So this equation is the equation of an ellipse. However, the exact calculation is harder to derive, and that is approximate result is energy diagram. For next case is planetary motion. Here we are going to solve the main problem of the chapter, that is the orbit for the planet, which is by gravitational interaction. We know that a planet and the sun interacts by gravitational forces. So capital M refers to the mass of the sun and small m refers to the mass of the planet, and the gravitational potential energy between them is given by minus g m small m by r, that is minus c by r. Alternatively, m could be the mass of the planet and m be the mass of the, in other words, you can also consider that capital M is for the case of a satellite moving around the planet, the capital M refers to the planet and small m refers to the satellite. Now, before we proceed with this calculation, it might be useful to consider whether or not this is a realistic description of the interaction of a sun and a planet. See, what are the problems in the approximation which we make in this video, and this to be considered before coming to the problem. However, most of the members of the solar system are neither perfectly homogeneous or not perfectly spherical. So the assumption we make that the sun is sphere or the earth is sphere, it is not exactly correct. For example, satellites around the moon are perturbed by the mass in the moon, and the planet Mercury is slightly perturbed by the. So, and also the solar system by no means is a two-body system. Each planet is attracted by all other planets as well as by the sun. Fortunately, none of these effects is particularly large. See here we are considering only the attraction between the sun and the planet. At the same time, that planet is being attracted by all other planets, but that is very smaller compared to the attraction between the sun and the particular planet which we are considering. So we just neglect it, but actually it is not a two-body system. So there may be small perturbations or approximations, may be some wrong. Most of the mass of the solar system is in the sun. So the attraction of the planets for each side is quite feeble, and the largest interaction is between Jupiter and Saturn. You can see the bigger planets, Jupiter and Saturn, they have the highest interaction, which is considerable when you compare the attraction between the sun and the Jupiter or the sun and the Saturn. And the effect of this perturbation is chiefly to change the speed of each planet, and so that the law of the areas no longer holds exactly. So here, so what happens is all these perturbations that is due to the other planets to this planet considered, and that will change the speed of the planets, and also the law of area will not hold good if due to the Even though there are perturbations and that doesn't shift the Jupiter by more than a few minutes of the arc, and also one calculates the planetary orbits. Please read this slide for more understanding. Yes, if a body is not homogeneous or it is not spherically symmetric, and that body's gravitational field can shown to have extra terms in other than the 1 by r square term, like 1 by r raised to 4, and the coefficient depend on the size of the body compared to the r over the span of the solar system. The higher order terms becomes negligible, although they may be important for a nearby satellite. Since we are only considering the interaction between the satellite and the planet, and the nearby satellite's interaction we are neglecting, and therefore the terms up to 1 raised to r raised to 4, 1 by r raised to 4 is only important. And in this case, we come to the expression for the angular displacement, which is of the satellite theta, and the initial angle is given by theta 0. The theta minus theta 0 is the integral of L integral dr by 2 into the expression inside the root is root of 2 mu er square plus 2 mu cr minus L square. The first term refers to the kinetic energy. The second two terms refers to the potential energy of the satellite. This is pure kinetic energy in the radial direction. This is the kinetic energy in the angular direction. And these two terms comes from the effective potential energy. And this integral will give you the angle displacement of the satellite. Accordingly, if we complete the integration, which is done as by you, which can be done by you as a separate case from mathematical knowledge, the angle of the answer of this integration will become arc sine, that is sine in, of this value, and finally the value of mu cr minus L square is again found, and again finally this is all mathematical calculations which we got from the value of r is L square by mu c 1 minus root of this expression is come. You can note it from this video, the expression for r. And after coming to the expression, as we start from theta is 0 is equal to minus pi by 2, and then introduce the parameters, the value of this minimum equilibrium position r0 of the or equilibrium radius of the orbit, initial radius r0, that is found to be L square by mu c, where c is the gmm, and the value of epsilon, which is the energy, is root of 1 plus 2 e L square by mu c square. And the dimensional parameters, actually that refers to the eccentricity of the orbit, which will decide whether the orbit can be circle or a hyperbola or an ellipse or a parabola. And there are various possibilities for the orbit of the satellite that depends on the values of E, L, and as C and mu are constants, the two variables possible are E and L. And that E refers to the energy. That means whenever there is a change in energy of the satellite, that will cause a change in the eccentricity, which will affect the path or orbit of the satellite, will change from hyperbola to ellipse, or ellipse to parabola, or ellipse to circle. And with this replacement and this equation, which is shown in the last slide, can be written as this is the, in terms of eccentricity, the radius of the orbit in general term is given by r0 by 1 minus epsilon cos theta, where epsilon is given by the eccentricity from this expression. Next slide. There are three cases possible, and on the basis of the values of the eccentricity. The first case is the the value of eccentricity decides the shape of the orbit of the satellite. So the cases are, first case is if the energy is very much greater than 0, in that case eccentricity becomes greater than 1, and if the eccentricity is greater than 1, the equation of the orbit has a form y square minus ax square minus bx is constant, that is a form of a parabola. As we all know, the equation y square is equal to 4ax represents a parabola, whereas y square minus ax square minus cx or bx represents a hyperbola, which is an orbit in the case of e greater than 0 or epsilon greater than 1. In the second case, if epsilon is equal to 1, in that case, when e is equal to 0, that will become parabola where the equation y square is equal to bx, and that means x is equal to y square by 2r0 minus r0 by 2. Since r0 and r0 are constants, the x is proportional to y square. This is a parabola. That refers to epsilon is equal to 1 and E energy is equal to 0. Is that when you can see the general orbit, accordingly the value of epsilon changes. This ellipse can become hyperbola or circle or ellipse or parabola, and that accordingly the value of the center or the focus changes. In the third case, when epsilon is less than 1 and greater than or equal to 0, the coefficients of x square and y square are unequal but of the same sign. That is a case of ellipse. So mostly the planets revolve around the sun in elliptical form, and this is the case which we observe normally for planets. But the satellites case is different because satellites can have the energy of the satellite can be changed easily, just like firing the engine. And since it is not easy for the planet to change the energy, normally all the planets follow this path, which is an elliptical path where the eccentricity is between 0 and 1. And the coefficient of, in this case, x square and y square's coefficient are not equal. If it is become equal, that will become a circle. But since they are not equal, they are just an ellipse. And the linear term in x means that the geometrical center of ellipse is not at the origin of the coordinates. And we know that the ellipse has got two foci, the semi-major axis and two semi-major and semi-minor axis, and two foci are there. And if we have epsilon less than 1, in that case the values of E possible are minus mu c square by 2l square, and that is minus of that, and that should be, the energy should be this and 0. Suppose if the energy is equal to minus mu c square by 2l square, epsilon is become to 0, and the equation of the orbit becomes circle because the coefficient of x square and y square are 1, and that refers to a circle, degenerates to a circle. So that means whenever the energy of the planet or the satellite becomes very, very minimum, and that goes to the limit of the minimum possible value, which is minus mu c square by 2l square, then in that condition the planet or the satellite starts to revolve in an orbit which is circular, in that is a degenerate case. This comes to the end of our video. Have a nice day.